here. So today we're doing a two-part lecture. The first part is implementing CNNs, and that should be pretty fast here because it's a short lecture. First of all, our little quiz question that no longer counts and is weirdly formatted for some reason. This is from the Andre Karpathy video, so hopefully you've been keeping up with that if you can. Oh wait, we're not in presentation mode. There we go. It looks nicer. So which of these architectures uses the inception module?
It was GoogleNet, I think.
Very good.
Yes.
Yeah, it's GoogleNet. Which is part of why the thing is GoogleNet is actually used a lot, or was until like Resnet was used a lot in actual applications. But the thing is, because it's so complicated and has such strange the whole thing is it's got it's not just a straightforward architecture. It's got all the specifics in it that make up inception modules. It's very rarely used for research because it's hard to be used as like a test bed. And in fact, what we'll be looking at a lot later, we'll be actually using VGG19, and that's because it's the best of or it's usually considered the best of the just standard convolutional neural nets, where the entirety of it is just layers of convolutional layers, or many convolutional layers all in a row, and there's nothing else fancy to it, really.
VGG19, if I remember correctly, that one was the one that has lots of very small convolution area, or whatever I forget what you call the size of the convolution things. But
the filters?
Yeah, it has lots of very small filters, if I remember correctly. Or am I thinking of one of the other ones?
I think that's about right. It's the main thing that defines VGG19 is the fact that it has 19 kind of blocks of layer, or 19 convolutional layers in it, versus VGG16, which has 16 of them. It's not much more than that. Like, yeah, there's hyperparameter tuning involved, of course, and that's what leads it to be very good at what it does. But like, if you look at all three of these, if you look at 19, 16, and AlexNet, they're basically all just convolutional neural nets. They have convolutions, and they have pooling, and that's about it. Versus these other two, which we'll talk about both of them later today. GoogleNet is, well, it's just weird. It has these inception modules, which are multi-parted things that can learn on different levels, basically, as it goes. And then you have Resnet, which I'm going to wait until we talk about Resnet, but that's a really cool idea. And it's one of those super simple ideas, too, because you look at like GoogleNet and it's super complicated, and then Resnet performs way better. And it's such a simple idea that it's surprising we didn't figure it out sooner, which is great. So yeah, today we're going to talk about implementing convnets and some notable CNNs. So here's a few of the layers we'll be using. Unless we're doing some weird stuff with like text or something, we're going to always be using our conv2d as our main layer. We also have max pooling is already implemented for us. Dropout, we talked about that before, but super, super useful. We also have this flatten layer. That's really good for when you're taking it from convolutional to a normal feed-forward, possibly for if you have a head of the network that you're using as a classifier. And then, of course, we have our dense layers that we've used quite a bit in the past. So here I've got some example code of a nice Keras CNN. Um, again, we're creating a model, and we're also defining this in shape here. So model, and we define our in shape, as well as our other hyperparameters. We have our loss that we've decided is going to be categorical cross entropy. That is very good for this sort of categorical classification. And then we're using the atom optimizer again because it's just really good. It's the best multi-tool of neural networks in a lot of ways. In certain applications, you can easily find like ones where other things are going to work better. Sometimes just stochastic gradient descent will be better. Sometimes that with momentum is better. Sometimes there's a thing called RMS prop that can be better a lot of the time. But if you just want to try something and get somewhat good results, Atom is going to do the best most of the time. Anyways, on to the fun part. We're going to add some layers. We have our Keras layers here, and a pooling layer down below. We have a number of filters that we're going to set. This is going to be, these are our filters, our kernels, whatever you want to call them, and this is how many we're going to zoom over to the image, basically. We are also going to define a kernel size. That is going to be the size of each of these filters. In this case, we've decided on 3 by 3. And for pooling, we're going to decide how big each pooling group is going to be. In this case, we've decided that they're going to be 2 by 2. So it's going to go in these blocks of 4, these 4 squares across the thing, and pool them to make them smaller. Also, note we are using relu here. Just like a normal layer, we still have these activations involved, which are helpful. We have flattening, which in this case is going to take us from our 2D grids to our 1D, basically, list vector thing. And at that point, we're going to be able to operate on it just like a normal neural net. So we can have our dense layer with our relu activation and our softmax for a classifier. And when you really think about it, while this whole network is operating as a classifier, really the classifying part is here. The part where we're actually deciding what is in each class is happening here. And everything up here is almost closer to a form of pre-processing, but it's an automatic pre-processing that the network's able to do, which is why it's not called pre-processing, it's just normal processing. This part is where a lot of the important computation happens, but where the actual classification, the actual deciding what parts go where, goes on here in our dense layer and then our output layer. Finally, we compile our network with our optimizer and our loss function. We can train it for 200 epochs I have here, and then we're done. So that is, this function here is fully the CNN programming experience, basically, which is nice because Keras just makes our lives super easy for that. We can just define these networks by adding different layers to them all in a row, and then run it and see how it does. And there are so many other options out there for things you can add. Keras is huge, so if you want to try some things, if you want to, especially on our current lab where we're doing a lot of that, a lot of the competition, it is probably worth looking into some of these. Different types of convolutional layers, different types of pooling you can try. And you can even use this lambda here to wrap a normal Python function as a layer and treat it like a layer, which can be fun for doing various internal calculations. Often certain types of like weird custom types of normalization. But yeah, that's about it for implementing CNNs. Do we have any questions there, or anyone want me to like go over this quickly again, or? All right, cool. I think we're good then.
Ah,
Oh yeah,
I
do we
see.
have a question?
Yes. So, you said that 32 is the outputted filter from the convolution, and then why do we do the convolutions at 2 times before doing the pooling?
Oh, so let me make sure I got your question straight here. So first of all, it was clarifying that this is the number of filters that are outputted, and yes, that is the number of filters. And why we do 2 of these before 1 of these, and that comes down to convolutions, as we talked about last time. They're the main thing that's doing the learning for us. Pooling doesn't learn anything. Pooling is just reducing the size of our data to be a little more manageable. So in this case, I'm doing 2 poolings because it's giving us, we can learn more from that. And I didn't really see a need to do have another pooling in the middle, and that's something you're just gonna have to test a lot of the time. But you'll see this a lot actually in like VGG, and pretty much every convnet is going to have some number of convolutions and then a pooling. So it'll be like conv pooling or something like that. In this particular example, I might not even need the pooling. It might do very well if I got rid of the pooling there. It's mostly just to show you guys how to add pooling to the thing. Does that help? Does that explain it?
Yes, yes.
Nice. Good stuff. Any other questions on implementing CNNs? Cool.
Yeah, so our input shapes are it's like a 3-tuple. Like there's a height, width, and then like a depth. But we still use a 2D convolution layer. So like, do you always use like a 1 dimension lower than the input like dimension?
Not always, like in every circumstance, but in images, yeah. In images, we're pretty much always going to do a 2D, and the reason for that is just that we're not really convolving through the different RGB levels. We're not trying to find too many patterns in the color, as it were. What we're more trying to do is recognize the image overall. So what's actually happening here is we're having different of these filters going over the different, or each of these filters going over the different channels. So each of those 3 dimensions that make up RGB are still going to be gone over, but they're going to be treated as if they're just another part of the image almost. Yeah. And we have 3D convolutions. We can do those, but usually those are going to be used more for like maybe I want to make 3D models or something. I actually had one student who, for the final project, what they ended up doing was making a generator that would generate 3D models. And honestly, it didn't end up working because That's a very difficult task to do for various reasons, but the results were still really cool. Does that cover it?
Yeah, thanks.
Nice. All right, let's move on to some notable CNNs. First of all, AlexNet. This one was huge just because it was the first. It lit the spark of ConvNets. Now these were around for a while beforehand. Um, there's a researcher named Jan LeCun who has been championing these for many years. But AlexNet was the first neural network that it didn't just fuel image processing neural networks in a lot of ways. It really got people excited about the algorithm as a whole, in many different fields. Uh, it's in this again. It's not the best network. There's a lot of ones who've gotten better since, but it was very much something that was new and blew away the competition, blew away expectations. Yeah, it was great for that reason, and in that it of course competed in the ImageNet competition, which we talked about in our little history thing, and again won by a huge margin. It had about 60 million parameters inside, so it's a big model. It's a big neural net. It did some pre-processing. It started with 256 by 256 by 3 images. Anything larger than that was going to be resized and cropped to fit those dimensions. Grayscale images would then be mirrored into through all 3 channels of RGB, so they'll be still 3 channels, but they're going to be grayscale still. And then AlexNet also, previous to running it through, took numerous random crops of each image. So it would take different squares of the image of this size here, and that would actually be the real input to the network. And that's kind of data augmentation. You can actually do it pretty easily these days, but it's a cool little point into how it worked. And once it has these 227 by 227 inputs, this is the basic architecture we're doing here. We would do a convolution, stride of 4, then another convolution, or actually this one's a pooling, yeah. Do a pooling with a stride of 2, convolution, pooling, convolution, and then a bunch more convolutions and pooling. And as you can see, it's still following this kind of structure that we've seen before, where we're getting, in this case, it's showing it along the length. Usually I've shown it as like depth backwards, but the images are getting smaller and smaller, but there's more and more of them as we go back, until we eventually get down to these little tiny 6x6 images, in which case we can finally put it into fully connected layers. AlexNet had 2 of those, 2 hidden fully connected layers before we got to our output. And yeah, good architecture, did very well. Then we move on to VGG. This is Oxford Designs, and there were 2 versions at the time. I believe there's more now. 16 layer and 19 layer. It was the runner-up in 2014, and it's considered to be a very good neural network in a lot of ways, especially for research. It has 138 million weights, so even beefier model, huge neural net. And the nice thing about VGG is the weights for that are publicly available. So that's another reason why research uses it a lot, because we can just take these weights that it's already learned from ImageNet and apply them to anything else. Use them as a starting point, basically. And in the future, we're actually going to be using that functionality of it in one of our labs, but that is for another time. GoogleNet, we talked about this very quickly. I said that VGG19 was the runner-up in 2014. That's because GoogleNet had an error rate of 6.67%, which is nuts. GoogleNet is great. It was built on something called LayNet, which is why it has the weird capitalization in there, because it was made by Google and it was based off LayNet, so they were clever with the naming convention there. And it incorporated this special module called the inception module, which could run convolutions of different sizes, and then it would stack the outputs of those. So basically, instead of picking one particular kernel size, we're looking at several different ones to kind of find one that works almost. And the nice thing about it, because it was because it had the system set up, it can learn so much faster, it could be a much smaller network. And in fact, it was only 4 million parameters. Remember, AlexNet was like, what did we say, 6 million? 60 million, yeah. So we went from 60 million to 138 million to only 4 million. So that was a great improvement in memory. Also, the weights for this are available online, but it's not as easy for research. Why is it not as easy for research? This is why. If you're thinking this looks complicated, that's because it is. We have starting off some like base level convolutions where we're just doing them normally, and then we have a bunch of these inception modules. So each of these red to greens here is going to be one inception module. And it has, you can see it puts the image through several different paths and then recombines it here. And in fact, it will end up having multiple heads that are kind of chosen from afterwards. But yeah, big network. More efficient, but big and complex to implement. And before we get on to our last one here, and so far the best, or the current state of the art, I would say, for image processing, I want to talk a bit about managing gradients. Big subject, but we're going to only talk about it for about a slide here. The idea of them is, as our networks get deeper, as we add more layers to our network, the gradient, the loss basically as we're moving backwards, that delta value that we worked with, is forced to get smaller and smaller during backpropagation. And the way you can think about that is, I think I mentioned before that anything that you can do with a multi-layer network with sufficient activations and stuff, you could do just as easily, not just as, you could also do with a single layer neural network, just a really big one, or a single hidden layer neural network anyways. But as making a wider network is less efficient. You can get the same amount of work done with a smaller network, fewer weights, but a deeper network, much more efficiently. So you'd think that what we'd end up doing is just continually making deeper and deeper networks. And the reason we can't do that, the reason that these neural networks can't get ridiculously deep, is because we have this vanishing gradient problem. As we get deeper networks, the gradient becomes smaller and smaller and smaller until it's not having an effect on the layers as we go backward. And sure, we can do things like try to multiply them by scalars and stuff, but that can slightly delay the problem and also cause its own problems. And really, there's not a great way of fixing this in a perfect way. There's no perfect solution to this one. But one of the important things to know is that the way it happens, or one of the things that most exacerbates the problem is deeper networks. As we propagate to earlier layers, these multiplications get smaller and smaller, and our gradient eventually gets infinitely small. So,
A quick question.
yep.
Are there any situations where you would want to have a learning factor that would change depending on what layer you're on?
Yes. What layer you're on. There are some. That is a complicated topic that I don't know that I can speak on right now. I'd have to look into it a little bit more. But yes, I know of a few that do something like that. More often, you're going to see things where the learning rate will change based on other things. Well, there's actually some where what they'll do is they actually have a learning rate not based on every layer, but based on every single weight. So that's more what you're going to see are things where there's a learning rate that is actually specific to every particular weight. So you'll have a full matrix of learning rates along with the weights that you have. That's a bit more common, but yeah, there are some situations where you could have layer specific ones. I can't think of any off the top of my head though. I'm sorry if that wasn't a super great answer, but
it is an answer.
It is an answer, yes. Yeah, so moving on from that, though. Resnet doesn't fix this problem, but it certainly resists it much better than any other network really does. It has something called residual blocks, and these are really good. These, and a super simple idea too, deceptively simple almost. Basically, you have a block of convolutional layers, and you have your inputs going through there, running through the forward prop. But you also have a path that goes completely around that. It's going, so every one of these blocks has a pathway through it where various calculations are made, and a pathway around it that is going to be an identity function that you're giving the network. And that path around it, there's no calculation done there. It just goes straight through and lets the image keep going upward. And a lot of the rationale behind this is the fact that neural networks aren't actually very good at doing an identity function. They're pretty good. They can be pretty good at it, but it takes a lot of calculation just to do that, when in a lot of ways it would be easier to be able to move your input through layers of the network. And what this allows, you can almost think of this as allowing for a neural net that can train from the top up. So instead of having your neural network learn knowledge about its input at the bottom and then have to try to, if the neural network ends up being too deep or something, has to actually get that knowledge to the top effectively, it has to retrain all of the top weights all the way down to the bottom weights. It has to fully train the network, basically, to be able to access things on the bottom. But the way a ResNet works, you can train something on the bottom and then have it move all the way to the top just by selecting from the skip connections. Changing the skip, by paying attention to the skip connections, you can basically have a network that grows. Think of it as a growing network almost. But instead of actually adding more to it, adding more layers on top of it, which is something that sounds a lot easier than it is. It's not something that actually works out much. Instead of taking that route, you already have the layers there, and you let it grow in a more natural way by moving through these skip connections. And again, that can sound, sometimes it's so hard to explain these because they're so simple. It's almost best to show graphically, and I think I have a graphic in here later. Before we get to that, though, one thing to note is that the error of this ended up being 3.57% on ImageNet, which is actually higher performance than a human, which is interesting. So if you put an untrained human in front of ImageNet and told them to say, what is this image? What is this image? What does this one belong? Which class does this belong to? A human is going to perform worse than Resnet, which is interesting. Yeah, I didn't have a graphic, I have a video. We're going to skip the video, but I suggest watching it later. It will show it a bit more graphically, but we're not going to be working with Resnet too much in this particular class, unless you want to do it for final project, in which case that should be interesting. But yeah, take a look at that when you have a chance. Resnet, the main thing you need to know about it is it has those skip connections, and it lets you, because of that, it resists the vanishing gradient effect, and therefore can have really, really deep networks, which is why it performs so well. It just has a ridiculous number of layers. So, any questions on anything from this first slide set here?
Not quite about this, but I was curious about the final project because you mentioned it a few times.
Yeah, I can answer quick questions on that, but I'm not going to get too specific yet on
it. Is that just whatever we want, essentially, as long as it uses these neural networks for images and things like of that nature?
Yeah, so it's, first of all, it's a group project, so you don't have to be in a group, but it's best as a group project.
Okay.
And I think there's some degree to which we'll be making you work in groups just because we're going to run out of time for presentations otherwise. The interesting thing, though, with it is, so what we'll probably end up doing, what we did last time is we actually said, okay, here's a list of projects you can choose from. And I think there were some good things about that and some not great things about that. So what we're probably going to do this time is give you that option, but if you want to do your own project, you can too.
Okay.
But that will be decided more later. And we're actually going to go to the next lecture now. But hold on to that thought, because we're going to talk about the quiz for today, the proper quiz on there, and it is somewhat related. So now this is such a fun lecture. This slide set is one of my favorite. There's like 3 that I really like in this class that are some of my favorites to go through, and this is one of them. First, though, if none of you know this one, that's totally fine because we've combined this into one lecture this time around. But what is a saliency map? Does anyone know what that is?
It's like a heat map for the image that like shows like which pixels are more important for classification, I think.
Very good. Classification is the only word I would change there. It's the pixels that are important for whatever task is being used. So whatever the neural net's doing, basically.
Isn't that the one that's generated that you can cover part of the image and you just move that part that's covered around and you figure out which ones will cause it to cease to activate or whatever it was?
Basically, yeah.
Yeah.
Um, so who answered those ones for my little extra credit log here?
Michael Lee.
Gotcha. Good job. Uh, here we go. So here we go. We're gonna see a neural net art show now. Does anyone know what this is?
It's a squirrel slug.
Is that Deep Dream?
It's it's either from Deep Dream or from another similar sort of thing. I know that I hate it. I can tell you that much. Um, it's terrifying, and I think it might be one of the old lost ones from the Cthulhu mythos or something like that. But
Eldritch
yeah,
being
yeah,
equipped of immense power.
It was one of those monsters Godzilla fought.
yeah, it's terrifying. And we also just have, like, if you look closely, I didn't notice this until recently. There's recursive cities also going on over here, also made of animals. So that means that this thing is actually huge. Um, also, is this like a granny? Is this like a
Yeah.
granny over here?
It looks like there's two people in the bottom left corner, sort of on a cart
Yeah.
or something.
I was
Yeah,
gonna say
that's
it's like a car. It's like a street.
yeah, that's
view
part of the
something in
recursive
Paris or
cities
whatever.
here. That's part of the recursive cities. Um, so yeah, this is something. We can also look at some of these. These are the activation maps of the inside of neurons, and these are specifically ones that ended up combining two classes. So we have a dog that's also an admiral, I think. We have a pig snail, always fun. Camel bird, dogfish, just nothing that needs to be around. The Batman, except he's made of eyes. This would be something. This looks like that scarecrow drug thing they had in the first Batman Nolan movie. Um, I hate it. And then we have also made of eyes or maybe nebulas or something. Mona Lisa. That one. These ones are definitely from Deep Dream, by the way. Um, but yeah, we're not done with those. We have more of those to come. But now we'll get on to the actual lecture here. So, image processing. We've talked about it before. I would hope we have. The class is called image processing or neural image processing or whatever. And we've talked a lot about classification. But that's it. We haven't really talked much beyond that. And today we will finally fix that because classification is just one tiny, tiny part of this. Image processing is any way in which we're going to be changing images or analyzing images or anything like that. We might need to get information about an image, like classification or segmentation. Talk about that in a bit. Or we may need to generate completely new images. We might need to do some combination of those. But the important thing to remember, these neural networks are still just function mimics, and therefore we can apply them to any function. If we can phrase it as a function and treat it like a function and find training examples to train it that would follow that function, we can apply a neural network to it. Will it work? Who knows? But it will certainly try to work. We just need inputs and expected outputs. So, of course, we've talked about classification quite a bit. We have our class labels Y, our data records X. X will usually be an image, while Y will be some class, maybe dog or cat, maybe 0 through 9 for data images or digits, hand-drawn digits in MNIST. Very big area, but still just one area. And pretty much all the best results from that are just going to be normal consnets with a head at the end that's going to be a feed-forward head, and that's what you have. Lots of types of classification. A lot of the times we'll use probabilistic of some sort, but that can either be binary or multi-class, and various things about your network will change based on that, such as what loss function you're using or how many neurons you have in your output layer. There's also deterministic binary and deterministic multi-class, where we are actually selecting a particular one. It's also a major part of this. Oh yeah, this was one I did a while ago. This was bad. This didn't go well. This is a project I made that was I like to phrase it as it's a neural network that tells you how ugly your cat is or your dog is. Basically, it would have to predict how soon an animal would be adopted based on a data set. And yeah, that's what it did. It would just take in images and it would take in tabular data and it would try to combine all of that and see if it could predict the likelihood of animals being adopted. And it did not do very well. I can tell you that $25,000 is not something that I have any part of these days. But it was a fun little attempt. It did the job. So now let's just let's dip our toe in the water to not classification, and that's just going to be classification plus something else. Given an image, let's see if we can not only figure out what's being shown in that image, but try to create a bounding box around that item. That is called classification plus localization. And the way that's going to work is you have the image, you got to put the box around the cat and tell us that it's a cat. There's also two other variants here that we aren't going to look too much into, but they're important. Object detection is one. This is actually what the ImageNet challenge is object detection. It's not actually classification. That is just this classification plus localization for every object in an image. So you'll see in this case we have cat, duck, dog, and the duck is a fake duck, but it was still able to figure it out. And then if we want to get really nitty about it, we can say instance segmentation. So this is going to be, we do the same thing except instead of a bounding box, we're actually going to try to draw a n segment polygon around this thing and see if we can get a fairly good bound for where the object is in the image. So how do we do this? Let's start with classification plus localization. What we can do is, remember, we're talking about functions here with example inputs and example expected outputs. So all we really have to do here is have outputs for the number of classes. Let's say if we have 3 classes like dog, cat, duck. We have those and one output for each of those. And then we're going to have 4 other numbers for outputs that are going to describe the box. This can be X, Y, W, and H. You could instead do the 2-point method where you're just doing 2 diagonal points of the box. Doesn't really matter how. It's going to be able to figure that out pretty easily. As long as you add those outputs in and include those in your backpropagation, it should be able to create that box as well as classify. So that's kind of nice. As long as we have we can, instead of trying to come up with ways in which these convolutional nets are going to come up with an answer that we like, what we can do is just make the network, add the capability to give us those answers just by adding outputs at the end, and then see if maybe just training it that way is going to give us the results. And a lot of times it will. Again, you need that data. You need to have training examples that have these boxes drawn on them already. But that's not that hard to get. Don't think there's all that much more to say on this slide. This is the main sentence here, though. Basically, we structure the output and the data and let the CNN figure out how to mimic it. It's the beauty of it. We might want to make some changes, though. For example, let's say we want to evaluate how well we did for localization. We could do something like accuracy, or it's harder to do something like accuracy, though, because we're trying to draw a box. Like, they can be a little bit outside the box, or So what the way we're going to evaluate these is through this intersection over union metric, in which case we're going to take the area of the overlap, how much of the two boxes that are drawn between the real box and our generated box, how much of that area overlaps over how much of that area is there in total. And by doing that, you can get a pretty good look at how well you're doing. And in fact, if you end up being completely overlapped, if the boxes are absolutely the same, then you're golden, because then you have an intersection over union of 1. And that is perfect score. That's what you're going for here, is your big 1.0. So, we have our fully connected layers for localization and classification. We want to keep these parts independent. So when we're doing our final thing, when we have our heads there, instead of having like two hidden layers and then one final output layer, we're going to have 2 hidden layers and an output layer for each. And that's because it's going to be a lot easier for the neural network to learn the specific box drawing function as the one head and the classification function as the other head, instead of trying to learn both at the same time. The part that can be shared, though, is the convolutions. Those will be just fine being kept together, as they're do a much better job of feature extraction almost anyways. So we're sharing our convolutional component, and we are splitting up the rest. Object detection and segmentation are a bit more complicated, and we'll often use other types of networks included. We're not going to be covering them much in this class, but they exist, and they are following most of the same patterns that we've been using for the rest of these. Human pose estimation. This is actually something that is often used as a step in other networks. But you can estimate what a human is going, from a picture of a human, what their position in 3D space is. And this can be done by having K segments that make up the skeleton. And basically all you're doing is training your neural network to see that image and define the different points that make up those K segments. And it's able to do it pretty well just by that, just with the normal convolutional. Usually you will end up having other parts to it as well, but it can do pretty well just like that. Depth estimation. This is actually the project that got me started on writing this course way back 2 years ago. Given a single normal 2D image, can we create either a 3D image or like a 3D heat map showing the depth of the image? Can we learn depth from the image? And yes, we can. Here we have several images, and we have a ground truth that was established with, I think, a laser. I think they had laser distancing for these. And here are the predictions we got. And we can see they're not perfect, and scale can often be off. Like over here, we have a kind of orangish part at the farthest. And here we have deep red. So it thinks this is much farther away. This bookshelf back here is much farther away than it is. But that being said, it gets the relative scale pretty well. It just, the global scale can be a bit off. And you can see it does pretty well in all of these. It matches pretty closely with the ground truth. A lot of options for this. One of them is to have, you're going to have several blocks of these convolutions and poolings that downsample the data, and then a little bit of fully connected layers in the middle, and then it mirrors up to extrapolate into a larger image. That use something called up convolutions. And notably, this entire concept is something called an autoencoder. And we actually have a lecture on that later. But this idea of downsampling an image and learning how to bring it down into this middle layer, and then learning how to bring that middle layer up into an image again, but a different image, is a huge area. It's a great tool to have in a lot of ways. And another example of how these networks can be creatively applied. But I'm not going to talk too much on autoencoders because that's for a later date. Up convolutions are a big part of those because then we can actually make images bigger as we go instead of smaller. Again, we're just working with matrix operations though, which is nice. Image generation. This is a good one. If we've shown our neural network a bunch of images, can it create its own images that are similar? And of course, we've seen this already, and we get to see more of it. Here we have many apple stands. This is just infinite apple stands, and it's going all the way back, and it's terrifying, but also probably pretty good.
Man, I could have got an apple there.
I know, right? You could have gone to the infinite apple stand. This one's pretty cool. This is one of the few that are not terrifying and instead are kind of cool. It's like some form of temple or something. It's created in mountains. I like it. It's a good fantasy setting. This again, I hate it. This one's uncomfortable. This was a neural network that was made to do what we were talking about, but instead try to combine two things. So this one was a tarantula and a gorilla. Not a pleasant combination. And I like tarantulas too. I used to have several pet tarantulas. I still don't like any part of this. There's a space shuttle in a church. It's pretty techno. Yeah, fun stuff. This is an eye traveling through space, except in this case, so this one it doesn't look nearly as terrifying. It looks kind of, it looks cool, but it's not as Lovecraftian. But that's because I lied to you. This is not from a neural network. This is from something called a genetic algorithm. Also generated, which is cool. And genetic algorithms are cool in their own subject, but if anything, this is proof further to me that neural networks are the main reason, the main terrifying thing here. And for further evidence of that, we have this image here. This is a city made of animal pieces. The world's made of animal pieces. There are clouds made of birds and horses and such. And there's eyes everywhere, and there's big-headed people riding cars. And this building seems to be in movement as it has legs.
Max,
Yep.
Max, this is Gustavo. Yeah. Well, I will have to go now. Just yeah. You used to show the a demo by, I think his name is Zelinsky, where he shows the activation maps for a convolutional network. That is the link that you recommended people to see, right?
Yeah, we'll probably look into it at the end of this.
Okay, that's good. Okay, well, thank you very much. Talk to you later.
No problem. Oh, and I sent you an email about the thesis.
Yeah, I will answer it. Okay, cool. Take care. Bye-bye.
Awesome. Bye-bye.
Thank you. Bye.
All right, so that one's terrifying. Oh, here's a blast from the past. Is it gold and white, or is it blue and I don't remember the colors, but all I know is really it's just a dog. That's just the whole dress is a dog and like a bird. All terrifying. And we got a little more. And yeah, they're all horrible, but like really good, well done, but terrifying. So how do we actually make images like that? That seems really difficult, and it kind of is. One of the most effective ways right now is using something called a GAN. This was made in 2014, is when that algorithm came out. And that is a generative adversarial network. This is a lie where it says that we may or may not touch on them. We absolutely will touch on them. We have a lecture for GANs. But quick summary. We are very good at making neural networks that can tell whether something is part of a class or not. We've done that before. It's just a classifier. So that's helpful. We can tell whether an image is actually part of a class. But generation's a bit of a harder task. We want to generate images, but we want to also be able to see how good those images are so we can do our backpropagation on them. So the solution for this is we can actually put two neural networks together and have them, in an adversarial sense, fight each other and end up both getting better, hopefully. So what we're going to do is we're going to create one neural network, a CNN, and we're going to call that the discriminator. It's going to be a classifier that discriminates between real images and fake images. That's its entire job, is saying, okay, this is a real image or this is a generated fake image. And we're going to have another CNN called the generator, and all that's going to do is take in as input a vector of noise, just random noise information, and it's going to output an image, and that image will hopefully end up being an actual image, or the image that we're looking for. And what you can think of its goal really as being beat the discriminator. Get the discriminator to label its images as real even though they're not. So here's what we have for that. We have a bunch of real images and a bunch of fake images that the generator will continually be creating from this noise vector here. And those fake images and real images will then be shuffled in, and the discriminator will try to beat them, and then when it fails, it will be trained, or the generator will be trained. And when it succeeds, same. Now, there's some tricks to this, there's some difficulties in this. Specifically, if you train the classifier has a much easier job, so you can't train it all that quickly. You need to actually, in fact, switch off between which ones you train a lot of the time. You can't have the you want the generator to learn a little bit faster because it has a harder job to do of creating whole new images versus the classifier, which just has to tell whether it's fake or not. So the generator we're usually going to end up training it more steps per training cycle. You can't be too crazy though, because the opposite can happen too. Basically, you need to have a stalemate constantly kept, and that is very difficult to do. And that's why GANs are notoriously hard to train. It is very difficult to have a GAN that you end up getting a good result from. But when you get a good result, it's a fantastic result. It does very well. So we're going to talk more about those later, and we'll actually implement one in lecture, but not right now.
Quick question about that. You were talking about how it takes in random noise. Does the type of noise that you use have any bearing on the results?
It can, but not really. Usually, if you just get a sufficiently large vector of random noise, it'll do. But it shouldn't matter too much. And it mostly just matters that it changes. Because otherwise you're going to end up getting the same image every time. And what you want the neural network to do is internally learn that it's just getting random data and finding a function inside of itself that maps that to an image that's going to be accepted by the discriminator.
Okay.
And yeah, I said before, this was only invented in 2014. And when I had this slide in when we first started this class 2 years ago, and it was a lot more. It had a lot more impact saying it only started in 2014 then, because it was only 2018. Nowadays, that seems a little bit longer ago, but still, we're on the cutting edge of a lot of this stuff. A lot of the newest things are, huge innovations are happening every day in this field, which is pretty great. If you want to, before we get to lecture, look into that too. We have this link here. This is a great little Towards Data Science article on it, and they give you Keras code. But we'll also be doing that in lecture, so that's fine. Caption generation. Hopefully we'll have a lab for you on this as well. We'll see what happens there. But given an image, can we generate a good descriptive caption for it? And yeah, we can totally do that. The way we do this is actually an interesting combination. It's going to be a lot like our autoencoder we talked about before, where we have data going down and getting smaller into a smaller fully connected layer in the middle, and then expanding and getting bigger on the other side. But the difference is, in one side, we're going to have a CNN. It's going to be the encoder. It's going to take the pattern, and it's going to learn how to get it into that small little vector in the middle. And then the decoder is going to be an RNN or some other text-based, something that can learn sequences and text. Maybe LSTMs, maybe GRUs, maybe a transformer. But this model is going to try to learn this captioning by taking the image and then outputting the text through this autoencoder. Again, this was a super cursory explanation because we'll be talking about this more later. But here we have more if you want to learn more about that. Again, though, we're using this cool autoencoder method, which is super helpful. And here we've our last thing we're going to kind of look into here is the same sort of thing we were doing earlier with, or we talked about this a bit before, how kind convolutional neural nets learn hierarchically, we can actually get those hierarchical visions almost of this from inside of this neural network by doing something called class maximization. So what this process is, what we can do is, do we talk about it? Yeah, cool. What we can do is, instead of do our gradient descent, but instead of descending, instead of learning on our weights, instead of doing this with respect, gradient of loss with respect to weights, we're doing gradient of loss with respect to the input. And specifically, we're doing that with a zero image, an image of all zero values. And this is going to have interesting results for us. What it's going to do is actually end up creating these activation maps of every particular filter in our convolutional net here. And that lets us see the hierarchical features as we classify something like a face, or object detect something like a face. So here at our higher layers, we're going to have whole faces. At our lower layers, though, we're just going to have lines that create these faces. So, however, you don't have to, in Keras, you don't have to do that, do the whole calculus for that either. You can actually just use these two functions, visualize activation, or you can do the similar visualizing saliency. And then, of course, is that heat map we talked about, which shows what parts of the network are important to pay attention to. But yeah, that's how you do that. Here's VGG19, using a similar situation where we have all the way up at the top here these very like textures almost, and then we kind of create more complex patterns as we move down the network and go to more higher layers in here, con 5.1 versus con 1.1. And that will eventually create things that are much more recognizable. That's all I had to say for today. Next week, we're going to start talking about style transfer, which is going to be the one of the bigger labs of this class.